will want to consider taking this class from dual credit through WSU Tech. Economically, it's a bargain, because basically you'll pay basically the same amount of money for this 5-hour class you would pay for the one credit class. And we'll talk about this, but if you're going into engineering, it won't count as your calculus-based physics, but if you're doing anything else, it's a bargain. But they're going to be here on Thursday to talk about that, okay? So just keep that in mind. Because some of you say, hey, what about that? They're in no big hurry. They're going to be out there on Thursday. So there's that. So today we're going to go through, finish up position time graphs, then we're going to do velocity time graphs, and then we're going to lab. So that's kind of how this deal will play out. Okay, so if you have a position time graph, and this is going to be in seconds, okay? So let's say I give you something like this, okay? So there's your position time graph. And I said, okay, what can you figure out from that position time graph?
It changed direction twice.
How many changes in direction?
2.
How do you know?
Because the slopes go opposite
You can see the,
twice.
Okay, now true or false? True or false? If the slope of a position time graph changes, the object changes direction.
False.
No, I mean
Eli, you
false.
shake your head no. Why?
So you can go at a different speed but the same direction.
Fantastic, okay?
True.
So if you look at this, okay, so here I'm coming down like this, right? So I'm changing the slope, but I'm still going in the same direction. Because the golden rule, if you're going to change direction, what has to happen to the sign of the velocity?
Change.
It has to change sign, right? So, which means if you're a math nerd, look for a relative maximum or a relative minimum, okay? Now, if you're like, Mr. Workamp, I like tangent lines. I love geometry. I love tangent lines. Nerd, but okay. So, we'll talk more about tangent lines later. But the short version of tangent lines, they touch a line only at one point. Okay, if you remember, like a circle, it only touches at one point. So if you can draw a horizontal tangent line, what that means is that instantaneous velocity at that point is 0. And that's what has to happen to change direction. Is that, we'll get this more into this when we get into the velocity time graphs. But if you're going to change the direction, there's 3 things that have to happen. So that if I take this apple, I throw it up in the air, it changes direction. And the 3 things that has to happen is that it's got to slow down. So on the way up, it's slowing down. And then it's going to stop. And then it's going to speed back up. So that's the sequence. So that's what's happening when you have a relative maximum or a relative minimum. So these lines are becoming more shallow. Eventually you're going to have a tangent line that's 0. You're going to come to a stop. And then you're going to speed back up. Now, true or false? If an object's velocity goes to 0, that means it changes direction.
False.
False. Why? Yeah, I could just be walking in one direction, stop, and then just keep going in the same direction. So just because my velocity goes to 0 doesn't mean that I change direction. But I can't change direction without going to 0. Okay. Now again, we're not talking about circles. Okay. We'll get to circles later. Completely different thing. Okay. Let's not talk about circles. Okay. So did I start at the reference point?
What?
Did I start at the reference point? No, I started at some distance. So maybe the apple is the reference point. I'm over here. Now, when you have a straight sloping line, and remember this for the lab today, when you have a straight sloping line on a position time graph, that indicates what type of velocity? Constant. So if you have a straight sloping line, that indicates that you have constant, hold on, velocity, okay? Now, what that means is that you're not accelerating. So that means that I'm walking along at the same speed all the time. So what you'll see is this is what it's called like a binary function. Either you can only do one of two things. you're either accelerating and your velocity is changing, or you're moving at a constant velocity and there is no acceleration. You can't, I'm kind of accelerating. No, you can't kind of be accelerating. Okay? Either you are accelerating and your velocity vectors are changing, or your velocity vectors are staying the same. Okay? So that's it. That's it. So if you think about it, when all of the problems that I'm going to write for you guys from here on out, here's the decision that I have to make. Do I want this thing to move at a constant velocity, or do I want it to accelerate? Okay, literally, every problem that I write, that's the decision that I have to make. And then, if I do want it to accelerate, I have to make a decision. It's a two-trick pony. Do I want the pony to speed up? Do I want the pony to slow down? That's it. Those are the only things I can do with every problem that I write for you guys. I decide, do I want it to accelerate? Do I want it to move at a constant velocity? If it's accelerating, do I want it to slow down? Do I want it to speed up? That's it. That's all I can do. All right. So I was moving at a constant velocity because I have a straight sloping line. I begin to slow down, change direction. Now, in this region here, I actually didn't mean to draw that as a completely vertical line. A little bit of slope there. So am I moving pretty quickly here or pretty slowly? Pretty quickly. How do you know?
It's steep.
It's a steep line, right? So the steeper the line, and this is a logic problem. Oh, slope represents velocity. Guess what? If there's a big slope, you have a
Big velocity.
There you go. Fantastic. With the big voice. Woo! Nick's all over that, or Dime was all over that one. He's like, wow. Ooh. Boom. With authority. Okay? So, there. Now, did I change direction at that point?
No.
No. What's the only thing I did?
Put 0.
Wait, what?
At this point, did I change direction? No. What did I do? I went past the reference point. So like I started, there's the apple, that's the reference point. I was over here, right? I moved away from the reference point, I changed direction, I came back, and then I went past the reference point. Okay? Then what did I do? I stopped. Then what? Turn around, and where do I end up? At the reference point. Okay? There you go. Got that. So either on your position time graph, you only have one of two options. You have a curved line and it's accelerating, or you have a straight sloping line and you have constant velocity. So if it's a curved line, you're either speeding up or slowing down. If you have any kind of sloping line, you have a constant velocity. And if you have a horizontal line, that just means you are
Constant.
at rest, and your constant velocity is
0.
0. Okay, you're just not moving. Okay? Those are the only three things that can happen. Now, let's talk velocity time graphs. That's going to be the part of the lab that we're going to do today. So we're going to do a velocity time graph. Something like this. So maybe that's 6 meters per second. Maybe that's 3 seconds. 4, 6, 7. Okay. So I got a new car, and I got the nerd package on the car, okay? Because I want my speedometer to be, instead of being miles per hour or kilometers per hour, I want it in meters per second, okay? So I said, come on, hey, yeah, let's check out the new car. So Jack goes, I'm all in, Rick, yeah. So Jack goes out, we're getting my car, and Jack happens to have a stopwatch with him, okay? So Jack's going to keep track of the time, and I'm going to look at my speedometer, not a velocimeter, okay, because I don't know velocity. I just know how fast I'm going, okay? So Jack's going to keep track of the time, and I'm going to keep track of how fast we're going, okay? So this is a velocity time graph. This is 0 meters per second, okay? 0 meters per second. So all I'm saying is that I'm going to start at 0 meters per second. My car is at rest. Again, I don't have to start at 0. The car could already be moving. I'm just going to start at 0 meters per second. So I'm going to say, at the end of 3 seconds, I know I'm going to be going 6 meters per second. I'm going to say, Jack, how long did that take? He goes, 3 seconds. So at this point, I have a data point. I have a point of 3 seconds and 6 meters per second. And here I am at 0 meters per second. So pretend that that's a straight sloping line, okay? Maggie, do you have enough information to find the slope of that line?
Yeah.
What's the slope of that line going to be?
6 meters per second over 3 seconds.
Which gets you?
2 meters per second squared.
Which gets you what physical quantity?
Acceleration.
Oh, 3 out of 3. Score! Okay. Physics snap. Okay. Okay. I kind of flipped out my honors chemistry class today because we went through like everything that had to happen to snap your fingers. And they're like, whoa, that's deep. Okay. It doesn't take much, but anyway. So with this one, you're going to take 6 meters per second minus 0 divided by 3 seconds. And Maggie goes, that's 2 meters per second squared. And that is my acceleration. Okay? So, what does the slope of a velocity time graph give you? Acceleration. Okay? Now, when you talk about acceleration, generally what we're going to have, anytime you have a straight sloping line like this is a particular type of acceleration that we call uniform acceleration. And that's what you always are going to have. Because if you have like curved lines on velocity time graphs, that means your acceleration is changing, and that gets real weird in terms of the calculus and the geometry and everything else. So you always assume that you have that acceleration is remaining constant over an interval. Okay? So let's look at what's happening. So I started at 0 meters per second. I ended up at 6 meters per second. Maggie correctly finds the acceleration. She doesn't give me the math answer of 2. She gives me the physics answer of 2 meters per second squared. So that was cool, right? I'm accelerating. And when you accelerate, for now, I only have 2 options. What can I do if I'm accelerating? What are my 2 options that I can do?
Speed up.
Speed up or slow down. Literally. So every acceleration problem that I'm going to give you, that's what I have to decide. Okay? Do I want Nick to speed up? Do I want Nick to slow down? That's it. That's the only thing I can do. Okay? That's it. So let's look at this. What's the sign of my velocity? Positive or negative? Positive. What's the sign of my acceleration? Positive. Am I speeding up? Yes. So this is on those lecture notes. But here's the story. Whenever your velocity and acceleration have the same sign, you speed up. Now, notice I did not say every time your acceleration is positive, you speed up. Okay? All I said is that your acceleration and your velocity have the same sign. They could both be negative, they could both be positive. So this is the first thing I want you to block out of your minds, and you'll see later why this works. That positive acceleration always means that you speed up. Okay? It can happen. Okay? You can speed up with positive acceleration, but you can also slow down with positive acceleration. You can slow down with negative acceleration, but you can speed up with negative acceleration. So the only golden rule is that if your velocity and acceleration have the same sign, you're going to speed up. So guess what? What's the converse of that then? If they have opposite signs, you're going to slow down. So if velocity and acceleration have opposite signs, you're going to slow down. Okay? And there is no exceptions to this. Zero, zip, nada. So I'm going to take this apple and I'm going to throw it up in the air. What did it do on the way up, Jack Rain? Did it speed up or slow down on the way up? Really?
It slowed down.
Okay, it's like, wow. That's weird. Okay, so as soon as it leaves my hand, what does it start to do? As soon as it leaves my hand, it starts to slow down. So what do you know about velocity and acceleration on the way up? They have opposite signs. Okay? There's no exception. So if you're defining up as being positive in terms of velocity, what's the sign of your acceleration? Negative. Now, on the way down, Jack, what does it do? Speeds up. Now what do you know about velocity and acceleration? Same sign. So literally, that's it. That's it. So no matter how complex the acceleration problem becomes, again, I have a two-trick pony. If I'm going to make something speed up, what do you know about velocity and acceleration? They have to be the same sign. There's no exceptions to that. If they have opposite signs, you are slowing down. So if you keep that in mind, that's the only thing that I can do. If I say, hey, this thing's slowing down, okay, velocity and acceleration have to have opposite signs. So if you know it has positive velocity, you know you have to end up with negative acceleration. If you have negative velocity and I'm speeding up, you know you have to have negative acceleration. There is no exceptions to that. None. Zero. Zip. Nothing. No exceptions. Okay? Now, come back up here. So I was cruising along and I was speeding up to 6 meters per second. Now, what's going to happen from this segment from right here? Now, here's the $1 million question. Is my velocity still positive? Mr. Houseman,
Yes, it's still positive,
how do you know?
because it's not, it didn't go below 0.
Didn't go below 0. Okay? Did not go below 0. My velocity is still positive. But I went from 6 meters per second to, say, 5 meters per second. So what did I do? Slowed down. Oh, Maggie. Acceleration. Okay? I don't want the number for now. Just tell me, is that little bit right there, is that going to be positive acceleration or negative acceleration?
Negative.
Negative. So this is going to be some, right in here, I'm going to have some negative acceleration. But, according to Mr. Houseman, I still have positive velocity. So what am I doing?
No.
Slowing down. So here I have negative acceleration with positive velocity. I am slowing down. Now, a lot of times what we're doing, you're going to do this on your lab today. You put in arrows indicating if something is speeding up or slowing down. So if this is your velocity time graph, you're going to put an arrow here that says, oh, this thing is speeding up. If you're slowing down, oddly enough, you're going to draw a down arrow. So I was speeding up, and then I started to slow down. Now here's the most common misconception. Kids look at this and go, oh, I changed direction because I went from positive acceleration to negative acceleration. Okay, and they think this is a direction change. This is not a direction change. The only thing that happened is that if I'm going to act this out, so I started at rest, I'm going to get up to 6 meters per second, and then I'm going to slow down a little bit. Okay? I didn't change direction because my velocity didn't change sign. My velocity is still positive. So as long as this velocity is above 0 meters per second, as long as I'm somewhere up here, I didn't change direction. Okay? I did not change direction because my velocity didn't change sign. Now, what do you think's happening in that flat line region? Fisher, what do you think's happening right here?
You're not moving
Why?
because your velocity isn't changing, so you're standing still.
Everybody cool with that answer? Maggie, you shake your head no. You should be shaking your head no. Why?
Because you're walking at the same.
Yeah. I'm just moving at 5 meters per second. Now, Fisher, you're partially right. Okay? Fisher, what's the slope of a horizontal line?
0.
0. What is, and the slope of a velocity time graph gives me acceleration. So what's my acceleration? 0. All this means is that my velocity is remaining constant.
Oh,
You would be right if I had a position time graph.
yeah.
Okay, but this is a velocity time graph. So when I have a horizontal line on a velocity time graph, that indicates that you are at, rhymes with constant velocity. Constant velocity, 10 out of 10. Okay? So, you're going to get, so when you have a horizontal line, that means that you have no acceleration. By the way, 0 meters per second squared is not an acceleration. Okay? That's like saying, I have no money in the bank, but I have money. No. Okay, if your bank balance is 0, you have no money. Okay? So if you have 0 meters per second squared, you have no acceleration. So if you have 0 meters per second, wait for it, you are at a constant velocity. So what I did is I started at rest, I sped up, slowed down a little bit, and then I'm going to move at a constant speed. Now, when I hit this point, what am I going to do?
Change direction.
No, just from here to here.
Oh.
Speed up, slow down.
Slow down.
Slow down. Now, there's two ways that you can approach this. Some people like different views. Some people, it's kind of almost a religious thing. They're looking for a sign. It's like, I'm looking for a sign. Good for you. So, you can look at signs and go, hey, in this region, I have positive velocity and I have negative acceleration. My signs are opposite. I'm going to slow down. Okay? So if you like signs, you can approach it that way. Some people like, Burkham, this represents 0 meters per second. So here's your other way that you can look at this. If this line is going away from 0 meters per second, what are you doing? Speeding up. If this line is approaching 0 meters per second, what are you doing? Slowing down. Okay? So you can either look at signs or go, whoa, I'm going away from 0 meters per second. I'm speeding up. I'm approaching 0 meters per second. I am slowing down. Okay? I don't care how you think about it. It doesn't make me any difference. But, when this line does cross through 0, do I change direction?
No.
I don't. Eli, you're very emphatic about that.
You should put it in reverse.
You stopped and then you sped up again.
But did I change direction?
Yes.
You sure?
Yes.
You can't tell direction from the velocity graph.
Real.
Velocity time graph.
Because, wait, I think I have an idea.
Oh, please do tell.
No way.
Because I was like thinking about this because I was like, oh, this is kind of confusing. But then I was like, oh wait, this is just like the position time graph, but on the y-axis. You know what I mean? So, because it's going meters
I'm
per
not gonna lie.
you don't get it at all because it's meters per second, like on the position time.
Yeah.
But you're just putting that on the y-axis of this one. So if it's a negative, that means on the position time graph, that means you're going away from the, what's it called?
Reference point.
From the reference point. So if it's negative on the velocity time graph, that means you're also going to the, away from it, right?
No.
No?
Kinda.
Kind of?
Kinda.
That makes me feel a little bit better.
That was a pity.
You're in the stadium, but you're not in the box seat.
I
Let's put it
feel
that way.
like, is that, am I looking at bad though?
Yeah.
Because like the velocity?
Because you're holding on to this idea that negative velocity means that you're going away from the reference point, and positive velocity means that you're going towards the reference point.
Oh wait, I don't think that.
You just said that.
I know.
But you said that.
She changed her mind.
Yeah, I changed my mind. Wait, so then, like, I'm so confused right now, to be honest.
Okay.
Oh my god.
This is why science teachers have flat foreheads. Okay. That was much more dramatic when I had like an actual whiteboard. I could turn around and pound my head on the whiteboard, but they took that away now. It just loses this effect. You can pound your head on a TV screen. That was cool. Okay,
Wait, so what's negative velocity?
hold on. Just stop.
I'm just confused. Yeah, I am confused.
Let's
Oh, that's my
reform-
bad.
Okay, let's reform the circle. Okay. Let's reform the circle. Start at the beginning. There's no circle. Start at the beginning. If something is going to change direction, what do you know about the velocity? It has to change sign. Okay? Does the velocity change sign when it crosses through 0 meters per second?
Yeah.
Yes. So
It changes direction.
it changes direction. Okay? Because what you'll see is there's three things that has to happen for something to change direction. You've got to slow down, stop, and speed back up. So that's what's happening in this segment right here. I'm slowing down because I'm approaching 0 meters per second. So that's like this apple going up. Okay, it's slowing down and it's approaching 0 meters per second. Reaches 0 meters per second at its apex, and then it's going to change direction, and it's going to speed back up. So this is what's happening here. I've slowed down, I stop. This is when the apple is at the top of its peak. And then I'm going to change direction. Okay? Now, at this point I'm speeding up. But at this point down here, do I change direction?
No.
No. What do? I go from speeding up to slowing down. Do I change direction here?
Yes.
Yes. So in this graph, how many direction changes are there?
2.
2. Every time a velocity time graph crosses through 0 meters per second, you change direction. So what's happening here is that I'm going to start and I'm going to move with some positive velocity, and then I'm going to maintain that positive velocity, and then I'm going to change direction, and then I'm going to speed up, I'm going to change direction again, and then I'm going to stop. Okay? Now, can you tell where I am relative to the reference point based upon that velocity time graph? No. I have no idea where I am now. I have no idea. I could be in Paris, I could be in Johannesburg, South Africa, I could be in this room, okay? All I know is that I have some positive velocity. And if I'm defining this direction as positive, I'm over here, okay? I could be here and have positive velocity, okay? I could be on top of the roof and have positive velocity. So the only thing I know is that I'm moving in a particular direction. And positive velocity does not necessarily mean that you're going forward. Negative velocity does not mean that you're going in reverse. It's just a direction. Okay? That's it. It's just a direction. So, again, if this line is going away from 0 meters per second, you are speeding up. If this line is horizontal, you have a constant velocity. If the line is approaching 0 meters per second, you are slowing down. If the line is going away from 0 meters per second, you are speeding up. Once you hit 0 meters per second, you can't go any slower. I've seen freshmen try. Okay? Freshmen can't even go slower than 0. You hit 0, boom, that's it. So if you're going away from 0 meters per second on either side, guess what? You have to be speeding up. Okay? Got it? Good? Great. Now, pretend that none of this exists. It's all gone. Might be easier for some of you. It's like, okay, it's gone. Okay? But just if you lose it, be able to bring it back. So, let's say that Topher has been working out, and Topher can now run at 10 meters per second. Okay? 10 out of 10, right? And Topher is going to run for 5 seconds. All right? So how can I represent that on a velocity time graph? How can I show Topher running at 10 meters per second for 5 seconds on a velocity time graph? Topher, is this like a disco move, or are you showing me you want a horizontal line at 10 meters per second?
Both.
Both. It's a disco. Oh, that's varsity. Wow, we need one of those mirrored spinning disco balls. Okay, no, we don't. Just say, if disco ever comes back in style, just say no. I'm telling you, okay? Because then you're going to get into polyester and it's bad. Okay. So I was live through the 70s and it wasn't good. Okay. So you have 10 meters per second, right? For 5 seconds. Does that show a constant velocity of 10 meters per second? Yes. Now, how would I show that on a position time graph? Well, what does the slope of a position time graph give you?
Oh,
Next
would it
over
be
there.
when,
Slope of a position time graph gives you velocity. So we could draw a straight sloping line, and that would have a slope of 10 meters per second. So what that means is that every second goes by, how far does Topher move? 10 meters. It's a rate function, right? Okay. So a horizontal line on a velocity time graph corresponds with a straight sloping line on a position time graph. Okay? Keep that in mind when you do the lab. Okay? So a horizontal line on a velocity time graph corresponds with a straight sloping line on a position time graph. Okay? Got that? Good. Good? Solid? Okay. Now, pretend that this is gone. We'll get back to it. Topher, you're going to run for 10 meters per second for 5 seconds. How far do you go?
50 meters.
50 meters? Everybody cool with that? All right. You use distance equals velocity times time. You took 10 meters per second times 5 seconds, and you got 50 meters. Everybody cool with that? You've been doing that calculation for a long time. Okay? Everybody cool with that?
Yes.
Okay. Now, I want you to pretend that you are in a geometry class. And you're going to have a dimension that is 10 by 5. How are you going to find the area of that?
10
10
times
times 5. You're
5.
going to get what? 50. And then up to this point in time, on August 30th at 12:29 in the afternoon, your life, up to this point, what have you been taught? How do you express the units for an area?
Square.
Something squared. Meter squared, rabbit squared, penguin squared, something. Okay? What's the dimensions? It's 10 penguins by 5 penguins. So we're measurement, but hey, you're going to get 50 square penguins, right? Meter squared, something like that, right? It's a valid argument. I can measure in penguins, okay? I know, well, it's like whether you want to stack them side by side or like head to toe, okay? But that's a valid measurement. It's like, how fast are you moving? I'm about 20 penguins per second. Nice. What kind? Oh, the emperor penguins, like really weird hair. Okay. So that's an option, right? And what's the area of the penguin colony? Oh, it's 50 square penguins. Okay. It's valid, right? So up to this point in time, everything that you have taught to measure area has been in something square. Now I have to undo that. Okay, you're going.
Oh.
Now, we're going to go back up to this rectangle. This looks like a rectangle. Check my math, but I think this is a rectangle. It's been years since I studied geometry, but I think this is still a rectangle. Okay? And here's the dimension of this rectangle. This rectangle is 10 meters per second high, and it's 5 seconds wide. And you're going, no. Sure it is. You're on a velocity time graph, and I'm going to say, hey, Dime, I need you to draw a rectangle that's 10 meters per second high and 5 seconds wide. Got it, Mr. Burkamp, I'm on it. There's a rectangle. How do you find the area of a rectangle? Length times width, right? I'm going to take 10 meters per second times 5 seconds, and I'm going to get, so what's the area of that rectangle? 50 meters. You're going, no, Mr. Burkamp, don't be silly. Okay? It's got to be something squared. No, it doesn't. I have a dimension of meters per second by seconds. That's it. Those are my dimensions. So what's measured in meters? Right? Let me give you a hint. It rhymes with displacement.
Displacement.
Oh, how cool is this? So the area on a velocity time graph gives you displacement. So that 50 meters is how far Topher ran. Now, let's say Topher changes direction and his velocity becomes negative 10. How would we represent negative 10 meters per second on a velocity time graph? Pretty simple. We come down here and go, that's negative 10 meters per second. 5 seconds. This area would be negative 50 meters. Okay? So this is why we say the area represents displacement and not distance. Because if it's distance, that's just a scalar quantity, and it's just a number. How far did Topher run? 50 meters. I don't know which direction that he ran. But if he says, hey, Topher ran positive 50 meters, and we define that, I know which direction that he ran. And then if he goes, oh, he ran negative 50 meters, again, now I know which direction that he ran. So on a velocity time graph, the area represents displacement. And it's between that horizontal, between 0 meters per second and wherever that line is. Okay? Got it? Good? Great. Okay. So on the lab, let me hand out the lab so you can kind of see what's going to happen. So stop yonder camera. We're good. I just thought about that. So you're going to need about yay much tape. This is critical. Yay much. Not yay in a skosh. Yay. Okay? If you screw that up, the whole lab's just wrecked. Okay? So you got to have that. Now there's two sides to the tape. There's like a metallic side and like the plain paper side. You want the metallic side up. So what happens is that you're going to feed this through. There's a little arrow. Guess what? That's the direction that you feed it through. So you're going to take this and you're going to feed it through. And then you're going to take a little piece of tape and then you're going to attach it to the machine. This is critical. Don't put it on the machine and then try and get the machine through the tape timer. Okay? It's not going to work. But Mr. Burkamp, it won't fit. Really? Okay. So I've had that happen. That's why I went there. I'm not really. It's a good step. Okay. So we're going to put this through. And we'll take a little piece of tape. Now, this is where you have to make sure that you know which direction the machine is going to go. Because you want it going away from the timer. You don't want to attach this and turn it on and then have it climb back, you know, like go in reverse and go up over the timer. Okay? Awkward. All right? So, that's why I said, make sure you know which direction it's going to go. Now, when you do this, there's an on-off switch. If you need instructions on that, there are so many other issues. So, like, what's the on-off thing? No, just step away from it. Okay? So, but there is two different settings. There's a 10 hertz and a 60 hertz. Okay? Anybody know what the hertz represents? And not that isn't like pain. Okay?
I remember them, but I don't remember what they represent.
Okay, it's what?
Like,
Use them in pre-calc.
Is this the international sign for vibrations per second? Yes. Okay, this is the international sign for vibrations per second. Or, my God, I'm a rabbit. Oh, my God. Okay, so, so, this is the international sign for vibrations per second. You have 10, which is like 10 vibrations per second. And then you have 60, which is like this, like 60 vibrations per second. Make sure that you are on the 10 hertz setting, okay? So what happens is that, make sure it's plugged into, okay? So now this is vital that you get this sequence right, okay? Turn on the spark timer and then turn on the machine. Okay, because we want this starting from rest. So what's going to happen is that you're going to turn it on, and oddly enough, it's going to start making little sparks. Okay, there's not a fire hazard. Okay, it's okay. So you got this going, and then you're going to turn on yonder machine, okay? And catch it before it falls off the edge of the table. So what's going to happen, and for those of you that are on the front, it's easy to see, but what's going to happen is that, oddly enough, it's going to make little dots, okay, where this thing starts, right? Then you're going to see the dots get progressively further and further apart as it speeds up, because you're making the dots at 10 intervals per second, and then what's happening is that you're pulling more and more tape through that in each interval. So that's why I said you got to make sure that it's on, making dots, then turn on the machine, okay? And make sure somebody catches it, because I don't want to study like acceleration caused by gravity yet. So don't let it fall. It's like, oh, look, gravity, that'll make it fall faster. No, okay? This is not like a gravity machine. It's a constant velocity machine. So what's going to happen is that you're going to have your tape, and what you'll see is you're going to see a couple of large dots. That's where that thing was going before it started to move, okay? So we're going to call that like the 0 point, okay? That's going to be, this is basically where we're going to start. So then what you're going to see is you're going to have dots like this, so on, okay? So on your sheet, we're going to measure this displacement in each time interval. So you're going to take a ruler, and because these are pretty small distances, we're actually going to measure and keep everything in centimeters, okay? Technically, we should roll it in meters, but it's just going to end up with a whole bunch of decimal places that we don't need. So we're just going to keep it in centimeters. So remember, on your centimeters, you have the whole number of centimeters, you have the tenths, you can estimate the hundredths. So make sure that each of these measurements are measured in hundredths. So here's interval 1, 2, 3, 4. So you're going to measure this distance between that first set of dots where you started and this. You can measure that out. And let's see. What is that? Oh, this is...
It was probably Miss Shorts doing her like thing lab.
Okay.
Yeah, they
Sounds like Kaylee.
Yeah.
So let's say that's 1.20 centimeters. So on your this piece of paper, that's how far you went. That's 1.20 centimeters. Now, the total displacement is how far you have gone from the beginning. Well, at the end of the first interval, guess how far you've gone? 1.20 centimeters. So on this chart, so you got 1, 2, 3. You have total displacement. No, you have displacement. My bad. You have displacement. Displacement. Then you have total displacement, and then you have velocity. Okay? So let's say on that first one, I'm just going to make up a number. That's 1.20. You don't have to write the units at the end of each one of these because I've got the units up there at the top. Okay? So it'll just save you some time. Don't rewrite centimeters every time. I know what they are. I put those up there at the top. So that's also going to be 1.2 because that's how far we've gone. 1.2. There we go. Now, to make this simple, we're going to assume that the velocity in that interval is how far it went per interval. Now, technically, this is an approximation because technically this thing was actually speeding up at the beginning and was probably going a little bit, it started at rest and it was speeding up. That gets the math real complicated, and it's just not going to be worth the hassle. So what you're going to assume is that however far it went in that interval is how fast it's going. So whatever that number is on your first interval, and this will only happen on this one, that's going to be the same all the way across, because that's my total displacement, that's also my velocity. Now, in the second interval, let's say that you went a little bit farther, because it's going a little bit faster. Oh, and now I measure that second interval. Now, when you measure that, don't measure back to the beginning. measure from here to here. Okay, so it's how far you went in that second interval, not from the origin, from this mark to this mark. So now I'm going to add that together, and I'm going to get 3.20 because I went 1.2 centimeters here, I went 1.2 here, I went 2 centimeters there, total displacement 3.20. So this is going to be like a running total of these displacements. Okay? Now, my velocity, that's just going to be 2.00 centimeters per interval. So this cell and this cell will always be the same. So let's say the next one, you're up to 3. Okay, I'm up to 3. That becomes 6.2. That becomes 3. Okay? So you need 12 intervals. This is why you need yay. Much tape. Okay, because if you just have like a skosh, not enough. You need at least yay. If you want to be on the safe side, maybe go yay and a skosh. But don't go yay and 2 skoshes because then you're just being wasteful. Okay? So you're like, yeah. Okay. Now, so that's what you're going to do as far as data collection. So let me kind of take you through what you're going to do. On the analysis, you're going to draw 2 graphs. Just take one piece of paper, and yes, everybody's doing their own, okay? So you're going to have a position time graph, and what you're going to do is you're going to plot, listen to me, total displacement versus time. So you're going to come along here, and you're going to have your 12 intervals along here. So you're going to go from 0 to 12, and then you're going to plot total displacement versus time, okay? Not displacement, but total displacement, because I want to know how far I've gone at the end of the second interval, at the fourth. At the end of interval 12, I want to know how far I've gone. So if this goes right, this should look something like this. You probably have a little bit of a shallow curve at the bottom, and then it's going to become pretty diagonal. Hopefully that's what it looks like. So why do you think it has kind of a shallow curve at the beginning?
Because it has to speed up.
Speeding up. What does the slope of a position time graph give you? It rhymes with velocity.
Velocity. I just blanked.
Okay? Yeah. So at the beginning, it's starting from rest. It's speeding up. Oh, maybe that line becomes a little steeper. When it actually reaches constant velocity, what's going to happen?
Reach a
No, it's gonna
constant
go diagonal.
It's going to be a diagonal line. Why?
because it's the same.
Yeah, what does the slope of a velocity of a position time graph give you?
Velocity.
Guess what? If your velocity is constant, the slope is constant. Okay? What's the only way it would turn into a flat line? It stops. Okay? All right. Now, then you're going to draw a velocity time graph. Intervals here, velocity here. Where do you think this graph is going to start? 0. Why? It's not moving. Okay? This graph is going to start at 0. What's it going to do? Speed up. Guess what? You're going to accelerate. You're speeding up. Now, if it is an actual constant velocity device, then that line should plateau out. Okay? There you go. Now, realistically, it's probably not. You're going to have some deviations in that velocity, okay? But it should become relatively constant. So it should, realistically, the line will probably go on that velocity time graph, something like this, okay? That's typically how it plays out. It's still relatively constant, but you just have a little bit of variance in that. Okay, so listen to everything that I want done. I said on the velocity time graph, indicate if the card is speeding up by drawing an up arrow, or if the card is slowing down by drawing a down arrow. So anytime that velocity time graph is going away from 0 meters per second, you put an up arrow. If that line is coming back towards 0 meters per second, put a down arrow. Okay? That's all you have to do. Do not make this complicated. Okay? Nick, Dime.
If it's constant, do we just not?
There's nothing to put,
Okay.
because it's not speeding up or slowing down. Now, when you get to number 3, indicate if the acceleration is positive or negative in each region by either using a positive A or a negative A. So, pretend that you're in a math class. If this line is sloping up, guess what? You have acceleration. If the line is going down, you have, that's all you have to do. Okay? You don't have to calculate it. Just indicate what it is. Now, when you get to number 4, I say calculate the average velocity for the entire 12 intervals. So, here's how you're going to do this. It's a simple calculation. You're going to take your overall position final minus your overall position initial, and you're going to divide that by 12 intervals. How are you going to find your overall final position? Where are you going to look? Yeah. Find the sum total of how far you went. What was the total displacement? Add that up. It's usually around 20 to 30 centimeters, something like that. Okay? So you're going to take your overall total displacement minus 0, and then you're going to divide that by 12. You're going to get an average velocity. Draw that as a horizontal line on that velocity time graph, and then you're going to draw it as a sloping line on the position time graph. Now, you have a whole bunch of questions to answer, okay? Now, when you get to 5 and 6, 5 and 6 are the most critical questions on this lab. So on number 5, it says, write an explanation to describe what can be deduced by the shape of the position time graph. Explain any changes in the slope. Why do you think in big bold letters I emphasize the word shape and change?
Because the shape changes.
Yes, that's what I want you to emphasize. Look at the graph, okay? Does the slope change? Does the shape change? Yes. What does that mean? Okay? You want to reference that, okay? Say, oh, it starts off curved. What does that mean? It ends up a diagonal line. What does that mean? Same thing is true on your velocity time graph. Oh, it starts at 0 and then it goes up. Oh, what does that mean? Oh, then it becomes relatively horizontal. Oh, what does that mean? Now, here's your overriding thing. I'm going to return you loose. Listen to me. Both graphs have to show the same thing happening at the same time. So if your position time graph is curved, speeding up or slowing down, your velocity time graph has to show you speeding up or slowing down. If your position time graph is a diagonal line, your velocity time graph has to be a horizontal line. Okay? Keep that in mind. You can't have one graph showing it speeding up and the other graph having it at a constant velocity at the same time. Okay? You only need to generate one tape per group, give the data, go to 3. There's like 6 setups back there.
Look, this is you. I didn't draw it. Do this. I can't tell it. Like, what's going on?